When we looked at solving linear systems, there were essentially only three scenarios that we could encounter. We could encounter a situation where we had two lines that intersected at one specific point. We could have two lines that were parallel to one another, meaning there was no point of intersection and no solution to that system. And then we could have a scenario where two lines were coinciding or overlapping with one another. So two lines essentially drawn on top of each other, meaning there's an infinite number of solutions. When we look at nonlinear systems, these cases are still possible. We could have two nonlinear functions that only intersect at one point, never intersect, completely overlap with each other, but we also have a lot of additional cases. We could have 2 points of intersection, 3 points of intersection, and so on. So we're going to need to make sure we identify all of our points of intersection in these types of cases. In example 1, we're told that the difference of two numbers is 2, and the sum of their squares is 10. We want to find those two numbers. We can set this problem up by translating these two statements. First, we're told that the difference of two numbers is 2. So if we let our two numbers be x and y, the difference between those values should be 2. And then we know that the sum of their squares is 10. That means if we took the sum of x plus y, but more specifically x squared plus y squared, so that we're taking the sum of their squares, that result should be 10. What we can do then is flip over to Desmos to graph these two nonlinear equations. Well, we've got one linear equation and one nonlinear equation. And find those points of intersection by clicking on either of our two functions, either of our two graphs, and we'll see in gray, and we can mouse over those points to see that they intersect at 3, 1 and -1, -3. So this gives us two different points, or two different pairs of values, 3, 1 and -1, -3, that would share that relationship. So we could substitute those values in to both functions, both of our statements here, and we would end up with true statements. In example 2, we're told that the product of two numbers is 9, so that would be x times y is equal to 9. And we're told that the sum of their squares is 18. So the sum of x squared plus y squared should be equal to 18. We can update that second function that we already had and change this first function to x times y is equal to 9, and see that in this case we have 2 points of intersection, one at 3, 3, and one at -3, -3. Again, this means we have two solutions. Our two numbers that satisfy these conditions would be x equals 3 and y equals 3, or x equals -3 and y equals -3. Keep in mind then that when we're graphing these nonlinear functions, we just have to look out for multiple points of intersection. There could only be one, there could be no points of intersection. We just need to make sure we're thinking through all those cases and visualizing the entire graph.